This is June 09, paper 2. John is studying the principle of conservation of energy. He carries out an investigation in which small steel blocks are allowed to slide down a curved track from rest as shown in the diagram below. Each track is highly polished so that friction is negligible. Each block has a mass of 20 grams. A block starts from point P, which is 1.8 metres vertically above point Q. So of course this 1.8 metres is going to be quite significant in any calculations we do. Part 1. Calculate the loss in gravitational potential energy as the block travels from P to Q. So you're going to write down your GPE equation equals mgh. And that's going to equal, now we have to change our mass into kilograms, and 20 grams is 0.02 kilograms. G obviously is the value of 10 in the earth, and the height is 1.8 metres. And when you multiply those out, you get 0.36 joules. And so there's 1 mark for your answer. And there's a mark for your calculation and a mark for changing that into kilograms and a mark for your equation. Now again, if you did miss changing that into kilograms, you'll only lose 1 mark. But again, it's not 1 mark that you really want to lose. What is the kinetic energy of the block at point Q? So if it has got 0.36 joules of potential energy here, and energy is conserved, then it should all be changed into kinetic at the bottom. So 1 mark for the answer. There's no calculation needed. The answer is 0.36 as well. Calculate the speed of the block at point Q. Show clearly how you get your answer. And so we know that the gravitational potential energy at the top is equal to kinetic at the bottom. This just becomes a kinetic energy calculation. So 0.36 is equal to half times the mass, again 0.02 times v squared. So to get v, I'm going to just work down beneath this. 0.36 is equal to half of that is 0.01 times v squared. So v is going to be equal to 0.36 divided by 0.01 and then the square root of it. So it's 0.36 over 0.01 and then the square root of the whole thing. And the answer comes out to be 6. So there's 5 marks for that and not very much space. And if you have to do some work on it beneath, do that. So there's 1 mark for your answer of 6. You have got 1 mark for showing this bit here. You have got 2 marks for writing down this equation and 1 mark for writing the actual equation at the beginning. So even if you haven't a clue where to go, if you can even get this equation down, you'll get yourself 1 mark. The second part of the investigation involved using a steeper track between P and Q and using a block of the same mass, but keeping the point 1.8 P 1.8 metres above Q as before. So the shape of the track is different. The other one was not as steep, but the height is the same. What change is there, if any, to the kinetic energy and the speed of the block as it passes Q where the track is made steeper? Assume energy losses due to frictional forces are negligible. Now, it says kinetic energy, and kinetic energy is going to be equal to the potential energy at the top. So the potential energy at the top hasn't changed, it's got the same mass, it's the same height, and therefore the kinetic energy isn't going to change either, so it remains the same as before. And if kinetic energy doesn't change, and kinetic energy equals half mv squared and m's the same, then v isn't going to change either. So it remains the same as before. That will get you your 2 marks. The final part of the investigation involves using a steel block of greater mass, but keeping the track between P and Q exactly the same as shown in the diagram above. What change is there, if any, to the kinetic energy and speed of the block as it passes point Q when a block of greater mass is used? Now, this time, again, the potential energy at the top equals the kinetic at the bottom. I'll write in the 2 equations down here. But at the top, you still are at the same height, but the mass is greater, so the GPE at the top must be greater, and therefore the kinetic energy at the bottom must also be greater, so it increases. The speed of the block at the bottom then, because the mass here is increased and the mass here is increased, when you put those equal to each other, the speed doesn't change. It just remains the same. If I just show you that, if I write mgh at the top is equal to a half mv squared at the bottom, no matter what the mass is, the masses cancel each other out when you do that calculation, and therefore it doesn't matter what the mass is. If you drop it from the same height, no matter what it is, you're going to get the same velocity at the bottom.